I begin the discussion on last week's assignments, let's just remember, I don't want anybody to ever say they didn't know the midterm was on Monday. It's next week. If you miss it, that's very sad. It's worth at least 5%. Is it, or is it 10? It might be 10. In other words, it could be worth a lot, so be careful. I think it is. 2 5s for the quiz, 1 10 for the midterm, 30 for the assignment, 50 for the exam. That's everything? Yeah, so it's 10. We're getting to the haggling over weights at the end of the semester. No, it's a little bit premature to worry about that. Right now, you should be focused on getting as maximal marks. And on that note, let's talk about what happened last week. Okay. All right, before we get to talk about what happened last week, let me first announce. So remember, I had promised you a bonus problem last week. So I gave it now. So what happened is, I had given you I had intended to give you that problem that I posted, but just the time that I had to travel caught up on me. I didn't get a chance to set it and test it and all of that. So it didn't happen in time. Now, this week was intended to be an empty week because your midterm is immediately next week. And in the policy of not giving you more than one assignment, more than one piece of assessed work in the same week, the idea was that if you're going to have a chance to study for the midterm, it should be this week, not next week. No point studying for the midterm after the midterm. So you will get a problem of the week assignment next week, and this week there is none. Except that since you didn't get the bonus problem last week, I put the bonus problem by itself in its own problem of the week this week, but it is entirely optional. So it won't count. It won't count if you don't do it. If you do it, it will add to your grade from last week, and that will be taken out of 50 total. So it would be as if you had it as a bonus problem on the same contest, except that you didn't get a chance to do it at the same time. Unfortunately. Anyway, all right. Now, I haven't had a chance to look at the leaderboard and see what the distribution looks like. So I understand that some reality hit some people last week. See, somebody. The reason why he's laughing like that is because, see, for them, what you had last week is how they felt from the start, right? So they were. So the thing is that he's just laughing at you because like, but that's not really intended. It's supposed to be challenging, and you just have been good enough so far. So I don't want to feel bad. No, I want to talk about, because as I said, I haven't seen a leaderboard and I didn't get a chance to kind of look at what the performance was like, what it might be indicative of. So given that we have, our normal 5 to 10 minute chat, I wanted to get from you what the issue was, and I can tell you how you should have done it or could have done it. Issue was what? Bad blockchain? What? The question, I don't like these questions up front, but I'll echo it so that you understand what I don't like. So the question is, at around week 8 or 9, are you going to start getting back these easy questions? So let me tell you why I don't like it. Because you see, in my opinion, I have seen not listened to the answer. In my opinion, I haven't changed the difficulty level at all. So I think that this last week's assignment, no, that's not entirely true. Both are medium, and previously some of them were easy. Yeah, okay, so that is a reflection of how I think the question is. But as far as I was concerned, in terms of what you've covered and what you're equipped to do, hasn't changed. So from week 0 come up to week 4, in terms of assignments, what I had in mind that you could use to solve that problem was just, to my perspective, just within your grasp, according to the medium or easy rating, as it has been from the start. So I have not deliberately tried to say, okay, shift gears now. It's time for them to feel some pain. Nothing like that. I just like, it's nothing like that at all. It's simply, here's, really? No. That's what I'm saying, it's not like that. So I'm saying it is simply, here's some more topics, here's some more questions on those topics. And you've been able to handle them so far. Okay, so you had one little stumble, that's okay. Let's talk about what the problem was. Bad blockchain. So you had a cubic function. And you had to figure out, so you might have thought you're supposed to figure out where is that cubic function equal to some value, but that's actually the same as a cubic function equal to 0. Okay, just set the constant and put it on the left-hand side. So you have a cubic function equal to 0. Yeah? You're trying to find the closest integer that would make that cubic function equal to 0. So how do you find that? Well, all right. If it were something like exponential or suppose the function had been, you can start. Oh, that's fine. Suppose the function had been like this. I don't know what kind of function that is, but you get the function somehow. And I'm asking you to find where is, what's this point here? That's what you're asking. That's what you're trying to figure out, right? And you have a way to calculate f, and it's quick. It's order 1 time to calculate f, right? You put it at n, you get f of n. Quick, right? It's not a big process. What's the procedure that you should use to find that 0 crossing? Algebra? No. You see, algebra is only going to work if you can actually solve it. But suppose you get some, I don't know, some funny function. Sine x squared plus 1 all over x cubed minus 1, I don't know, minus some horrendous thing, black box, that comes back in order 1 time. What you going to do? What's that mean? We have a technical term that you're not calling. Binary search. Use a binary search. Use a binary search. What if the function looks like that? And you want to find that point, what should you do? What should you do? Use a binary search. Right. So if the function looks like this, like every cubic does, what should you do? So therefore, what should you do? Yes, you need to use 2 binary searches, right? So find that point, find this point. So you're going to do a binary search in this region as if it's increasing. You're going to do a binary search in this region for the, where is it? Sorry. Oops. You want to find a binary search in this region for a decreasing function, and then in this region for another increasing. So the binary search here and here are the same, and the one here is one that you would use for this. Now, it is possible for you to write a single binary search that can deal with either, a little more complicated, but nobody can call you up if you write 2 separate ones, one for when it's increasing, one for when it's decreasing. You just deal with them separately if you don't want that headache. You'd still get full marks. So what was stopping you? Timeout? Why would you? You used binary search and got the timeout? No, they did it wrong. It's not binary search. Because a binary search is a log n time process. How are you running out of time? So you did use a binary search and you got the timeout on one case? Yes. That is interesting. That's very interesting. That means, no, okay. So, all right, look. You might feel slightly aggrieved that you didn't get the perfection. But if you only miss out by one test case, you can still pat yourself on the back because you actually thought of using, you actually tried to use the binary search, which is the right idea. Now, if one case doesn't work, then that means that, what does that mean? It's an edge case. Now you need to think about what are the edge cases here. Well, sometimes you draw a function, a cubic function, it don't quite look like this. You can have, what's that thing called again? That thing that turns and turns again. What's the point of inflection? So you have a point of inflection, the tangent line, the horizontal, you won't cut the, it's not increasing, so then your binary search might flounder a little bit.
Function was increasing, and based on that effect of taking how I've incremented the variable, such as
Wait. That's not binary search anymore.
yeah.
Okay. Oh, that was like, okay, in frustration you tried this other thing. Okay. It's okay. Yes? Can you use what? No judgment. What do you say? Only if you use the wrong binary search in the wrong region, you won't get anything. If you search binary search in this region, expecting functions to be increasing, you're gone. It's not going back. Then you get one of these at random.
And then you got the other roots in there.
So the problem with that is that the roots may not be integers. And so when you start doing that, then you get into the round off problems. Sorry? Okay. So, okay. So okay, if you know calculus, then if you know calculus, then you can differentiate the function, solve, get the turning points, and then you know where the boundaries are for the increasing and decreasing regions. If you don't know calculus, then you can explore the function. You can sample points and you sample adjacent point. And if the adjacent points differ by a positive amount, you know it's increasing. And if they differ by a negative amount, you know it's decreasing. And all you're trying to do is figure out where these three regimes are. And once you've gotten them, then at that point you can start sampling when is it negative, when is it positive, then you have your bound. Then you do your binary search in those regions. So even if you don't know your calculus, you could still do it. You just have to be, now you need one extra step of cleverness because you don't want to sample consecutive points. You have to jump around the function, sampling the points until you get everything you're looking for. It's increasing, decreasing, increasing, and negative, positive for the, or positive, negative, negative, positive for this region, positive, negative for the decreasing region. And you just really want those 6 points, and then you do binary search between them. Okay? So that's, in general, that's what I want you to keep in mind. If you're, this approach will work for any kind of function once, even if it's not well expressed mathematically, even if it's non-linear, as long as it's actually increasing or decreasing, you can take that approach. Sample it, look for the features that you're looking for, and if you're looking for a zero crossing, you want a negative and a positive value, do binary search between those limits. Okay? So it's better than trying to algebraically do it. Why? Because it works for more situations. The algebra will be fine if the function you have is nice and smooth and clean and then, you know, so the calculus could work in that case. But if the approach without the calculus is actually more general purpose, even though a little more tedious. All right? So don't forget this lesson now. You never know when it'll come back. You want it back next week? I thought that's what you just said. You just said you want it next week. All right, now I got to try hard. See if I can. That wasn't in the plan, but let's see. I'll see what I can do. All right. All right. So now on with the lecture proper. So we last talked about self-balancing binary search trees, right? And if you recall, the time for insert lookup and delete where h is the height of the tree. And then the other point was, in a red-black tree, this is what we proved last class, the height is on the order of log n. In fact, we proved that the height is bound between, I think, half log n plus 1 and 2 times log n plus 1. That detail is not terribly what we want to get focused on. What the big picture point is that the height is proportional to the log of the number of nodes. And this then, coupled with the previous result, means that now if we implement our binary search tree operations on a red-black tree, we would get the performance we're looking for. There's one detail missing from this though, because right now it's not sufficient to conclude that therefore a red-black tree, sorry, solves our problem of guaranteeing log n time performance. The reason is, all this says is that if you could maintain the red-black tree properties, because that was what this proof came from, given the properties that you have, you will guarantee that height is proportional to the log of the number of nodes. And so this says, if you can guarantee that that can happen, then you will get this performance. But it remains to be seen that when you actually do the insertion or the deletion, because those are the ones that change the tree, that in fact you can maintain those properties. That is not entirely obvious. That remains to be proven or established. So in this class, what we're going to do is look exactly at the algorithm for doing the insertion, and then we'll convince ourselves that actually we haven't changed. We have to modify it because the basic algorithm for inserting a binary search tree just talks about dropping the node where you would have found it, right? So you just basically do a search for it. You're going to come off of some leaf and say, oh, it's not here. You insert it at that position. Clearly, we need some more rules because now our red-black tree says every node is either red or black. So when I drop in a new node, am I supposed to put it in as red or supposed to put it in as black? All right. What? That's a great instinct. Why red? There's an easier reason. I mean, I'm not even sure what you just said. I didn't fully get what you just said. You might be right, and it might be hinting at the real reason. If you drop it in as black, what rule are you violating? Almost assuredly. Remember that fourth rule that says the black path length must be the same? If I just add a new node and call it black, I just change black path length to that leaf. So I guarantee it is no longer the same as the others. So you could never add it in as black. Okay, so to answer that first question, how shall we add it? We're going to have to add it as red. But we have constraints on red nodes as well. What are they? So therefore, if I'm going to insist on adding it as red, but the parent that I just added it to was red already, then I'm violating a different rule. So clearly, we need some rules to resolve these tensions. And that's what we're going to talk about. Good. So how to insert? We're going to do exactly what we just said. So let me actually just capture it. I put it in this bit? I'm going to summarize it here. So insert a new node as red. And then the second step is if a problem arises, so if what the problem is that if its parent is already red, then we're gonna find and fix its critical cluster. And what's this critical cluster, you ask? I'm gonna have to define that for you. So to obtain the critical cluster of the newly inserted node, you're gonna trace up the ancestral path, trace up the tree to the nearest black ancestor. And its nearest black descendant. So if I were to insert so remember our convention, we're gonna draw black nodes with a rectangle, red nodes with circles. Suppose that we had the thing is that, okay. All right. I wanted to bear in mind that what I'm going to show you now is possible to happen as a subsequent step. obviously, when we just start with this, if these are non-empty trees, according to the black path length rule, I would have to have black subtrees underneath here as well. But when I just start, when I just first insert a node, these trees are essentially empty. So I can have a red leaf and it essentially has two empty subtrees. I'm considering them back in this context. So then it would be possible in that case that when I now insert a new node, suppose for example I could insert it here. If the new node that's inserted, let's just for argument's sake, say it goes to the red, so this is our new node. Then the critical cluster in this context would be here. Oh. So of course, think about this. If this were empty, so here's another black subtree. If I put this in as brand new, fresh insert, then you'd think of it as having two empties. Yes? But what I want to try and draw a general picture for you, because the idea of the critical cluster is not pertinent only to the leaf level. It can be described at any level in the tree. So what I have to ask you to bear in mind is that this picture is something that could arise after we've done some steps of the insertion process. And because I haven't told you how the insertion happens yet, you don't see how this could arise yet. So this is a generalization of what would happen at the very beginning. So for now, what I want you to think of is that each of these red-black trees that are rooted black are essentially just empty trees. In that case, these are all leaves. This red one was a leaf, and that red one was a leaf. And we just inserted this new node and called it red. Okay? So now I'm trying to describe to you how you find the critical cluster, and this is the process. You're going to find, so this is the new node. You're going to trace up to its nearest black ancestor. That's this guy here. And you're going to pick up from there all the descendants between it and its nearest black descendant. That's what those words mean. Now, of course, when it's all empties, it just looks like pick up the nearest black ancestor and all the red nodes below it. All right, so I keep that in mind. Now, in general, there are two kinds of critical clusters that could arise. This is one kind. This critical cluster has 4 nodes. 1, 2, 3, 4 nodes. It's possible that when I was doing my insertion, maybe this black node didn't have a right child. And then in that case, the new node would have been a child of the left red child. And in this case, my critical cluster, so in other words, the right side of this black node would have had another black node. Then in that case, the critical cluster would have just been 3 nodes. It wouldn't have had 4 nodes. Make sense? CC is critical cluster, right? So a critical cluster can have there are 4 possible 3-node critical clusters. What are they? Well, in my picture, if that were my black node, I could have had a left red child and then I insert the new node to the left. That'd be one example of a 3-node critical cluster. But maybe the one I insert needed to go to the right because maybe it's bigger. So it could have been over here. For example, can you think of two more? Yeah, left grandchild, right? So in other words, yeah, originally maybe the red node was on the right side and the new node comes in as the left of that node. And I would have had a 3 node on that side. Or maybe it's to the right, then it would be a 3 node going down. So there are 4 possible 3 node critical clusters that I could have. How many possible 4 node critical clusters could I have? I showed you one on the board. Can you think of some more? How many you know? 4 in all. Where are the other possibilities? The new node could be to the right here, or it could be to the left here, or it could be to the right here. So 4 possible locations for a 4 node, 4 possible locations for the new node in a 4 node critical cluster. All right. All right, so now let's talk about how to fix it. And then I'll run some examples so you can concretize this in your head. So to fix, let's discuss we'll discuss the 4 node one first because that's easier. Okay? To fix a 4 node critical cluster, any ideas what you think you might do? Suppose you're making this up and you see a structure like this. What do you think you might be able to do to address the problems of this red inherit parent-child? Set a black in between these, but then how about if I change these to black and that one to red? What could go wrong with that idea? If the what? Okay, so I think that didn't change because I took one out of here, which was in all these paths, and I added one on each side. So I removed one and add one. So I don't change the total length, yes? Of black nodes, total number of black nodes. And I would have then solved this problem of red having a red child. This is not the root necessarily, there's a parent here. The challenge really is that red nodes can't have red children. So if I now change this to red, maybe I'm creating another problem higher up in the tree. Good. So that's why I drew this the general way. Because now you can understand that the new node may not necessarily be the one that was actually inserted. It could be as a consequence of doing this recoloring, we've ended up creating a critical cluster at a higher level. So how do you resolve that? You repeat this process. Find the critical cluster at that new position and fix it. So worst case, you have 4 node and then you fix it and it becomes another 4 node above it and another 4 node. So worst case, you might end up changing the root to red. Root is not allowed to be red, so what do? Change it back to black. Because when you change the root to black, it's adding 1 to everybody's path length. So you're keeping that the same. Okay? And in fact, that is exactly how the black path length gets to be increased on a given insertion. So to fix a 4 node critical cluster, recolor. I'm going to draw it. Recolor, and then examine and fix. In other words, repeat this process at the next level. Okay, how do you think you might address a 3-node critical cluster? In a sense, this one is a little more technical because now we have potential problems, right? We're gonna have to like move these nodes around. Let's examine the 4 possibilities for the 3-node critical cluster so that we can see what you might need to do. So we have 4 cases as we just discussed. That's one. That's a second. This one is a third. And that's the fourth. Now, if I am to label these 3 nodes, I'm going to put a label on them. S for smallest, L for largest, and M for middle value. You tell me in the first picture where that S, L, and M belong. What's the root? This root of the critical cluster here. Is that the S, the L, or the M? The L. Because it's the rightmost node, right? How about this one? And then this is the smallest. How about this case? All right. How about this one? This is the S, and this is the M. Good. But this one is to the right of it, so it must be bigger. But it's to the left of that, so it must be smaller. How about this one? This one is smaller than this one because this one is to the right, so this cannot be L. S. What this one? Yeah, this is the largest. And what's this one? All right, this is what? The smallest? How about this one? Good. Okay. The reason I did that is that when you fix a 3-node critical cluster, it doesn't matter which of the 4 possibilities you had at the beginning, how they end up all look the same. So they all transform to the following picture. It's a balanced picture like that. And obviously, if this is how it transforms, so notice that the black is still up here at the parent, the 2 reds are on either side. This guy is smaller, the one on the left is smaller than the one in the middle here, and this one is bigger. So clearly, if it's the same 3 nodes, the S, the L, and the M, then this must be the S, this must be the M, that must be the L. Now, how you get there depends on where you're coming from and will be determined by applying different rotations. So for example, if I'm going from the first case to this, how do I do that? How many rotations do I need and which rotation? That's right, this is a right rotation. How about for this second case? Not 2 rights. 1 left and 1 right. Where's the left gonna get done? From S to M. Yeah, so we do a left here, and then it looks like the first case. And then you rotate right like you would have from there. So it's a left first, and then a right. So it's 1 left plus 1 right. But of course, it's left at about the SM link. Sorry for the mess. And this is right about the subsequent. I'm going to call it that L. Okay, so the point is, you might need 2 rotations. I call it a double rotation. You might need a double rotation or a single rotation Either way, you can do it in constant time because the number of steps needed for a single rotation is a fixed number. It's like 3 assignments, depends on how you implement it. So to do a double rotation, maybe you need 5 or 6 assignments, but it's still a fixed number of operations. Yes? All right. How many operations did I need for the 4-node critical cluster? I just changed colors. I changed attributes of 3 nodes, right? So also fixed number of operations. So to do the fixing of the critical cluster, regardless of which size critical cluster it is, just to fix that local critical cluster takes constant time. The problem, of course, is that the 4-node case pushed the work up the tree because it might have created another critical cluster in the parent level. So it means that the total number of fixes that I might have to do could be proportional to the height of the tree, which then makes the extra work to fix the properties cost me an additional order h. But it was costing order h before. When you add order h to order h, what do you get? Still order h. So the total running time hasn't really changed as far as orders of growth are concerned. And so now we can conclude, in fact, yes, okay, now our insert really does run in order h time, and because we've conserved the properties, we know that h is going to be order log n. Got that? Now you need to see an example, or are you good? Okay, so let's try this. Here's an example. Insert in order. All right, so here's what we're going to do. Remember, remind me, what was the worst case? What was the worst case insertion order you could get for an ordinary binary search tree? No, not a performance. What kind of input makes it perform poorly? Increasing values or decreasing values. Let's check what happens when you do the same thing to a red-black tree. Let's see how it copes. All right? So let's stick some numbers in, like say, for example, 10, 20, 30, 40, 50, 60. You put those into an ordinary binary search tree, and it just looks almost like a linked list. We call it a generate tree. Yes? Let's see what happens when you start putting them into a red-black tree. All right, so the first step, insert the 10. Remember that red-black tree's root is always black. So we're going to end up inserting it red and immediately changing it to black. Normally when I show this step, I don't bother to waste time showing the first one being red and then change to black. Because even in terms of construction, you might even actually construct it that way. All right, how about inserting the 20? Where does it go? To the right. It says insert red. And then check for critical clusters. Do I have a critical cluster? No, I don't even have 3 nodes. All right, now insert a 30. Where does that go? To the right of 20. Now do I have a problem? Do I have a critical cluster? I do, because I have a red node having a red child. How do I find this critical cluster? I search from the 30 to the nearest black ancestor, that's a 10. I then pick up all the red nodes beneath it, between it and the subsequent black nodes. In this case, it's everybody. It's every node in the tree right now. So then in this case, I then determine that I have a 3-node critical cluster on my hands. And what's the fix for a 3-node critical cluster? No matter what you do, you're going to rotate it so that it ends up with the middle value being black as the parent, and the small and the large row. Now it's very easy to get into a mode where you're taking a shortcut without really understanding what's going on when you're dealing with these tiny trees. It's very important for you to remember that what's really happening here is a rotation. Because when you get a more complicated tree, where there are subtrees on all the sides, you need to know where to put them. And the way you'll know where to put them is that you must remember that you are dealing with rotations. So as long as you remember that and keep that in mind, you will be able to keep it straight. Let's do some more. When I put the 40 in, so already, do you see that it balanced? It's self-balanced? What happens when I put the 40 in? Where does that go? Now, do I have a problem? Sorry, there's a 20 here. The 40 goes to the right of the 30. Is everything hunky-dory or there's a problem? Okay, what size is my critical cluster? 4 node. What's to fix? Recolor. So when you recolor, what's going to happen? This 20 is going to turn red, and the 10 and the 30 go to black. 40 is unchanged. Can I leave it like that? Root has to be black, so I need one more change. So what just happened to my black path length? Increased by 1. Do you remember that rule that said if you have a black path length of k, the maximum number of nodes you could have is 4 to the k minus 1? Right? Well, up until here, my black path, what was my black height? 1. So therefore, maximum number of nodes I could have is 3. So you see how when I dropped in the 4th node, it forced the black height to increase by 1. Right? Okay, let's, we're out of time. You can handle the rest, right? That was a yes? Huh? Where does this 50 go? The right of 40. Is that okay? The 3-node critical cluster, right? Let me circle that for you. You go up to the parent, and nearest black ancestor pick up all its red descendants between it and nearest black. So to fix this, what happens? You're going to rotate, and what's going to come up and what goes down? I'm rotating left, yeah? So there's a 20 at the root here. There's a 10 on the left. This is going to be a 40, it's black, and a 30 to its left, 50 to its right. Very good. Can stop now? All right, I have one. Oh, I heard a beep. There's a time. It's okay. I think the tutorial takes it 2 steps further, and things get more interesting there. So when I put in the 60, it's going to end up recoloring, and the 40 will turn red, and the 30 and 50 will turn black, and that's still fine, right? What becomes really interesting is when you add 2 more nodes to this, because so I will then have a 4-node critical cluster on the right side. It's going to end up having turning, when you recolor, you turn the parent red, And then you're going to have a 3-node critical cluster involved in the root. That's higher up in the tree. When you fix that, just remember you need to do a rotation. Okay? And then you'll see what the final answer is. But that you can do in your tutorial. Any other questions? Final questions? If not, then I'll see you tomorrow. We'll discuss deletion.